With this section, we're going to begin a discussion on inference. We're going to begin using the idea of taking a sample and using the information we gain from that sample, drawing conclusions about the population. One of the things that we have to do first is discuss what we refer to as the distribution of the sample mean. Okay, so our objectives in this section are to describe the distribution of the sample mean when we start with a normal population, and describe the distribution of the sample mean when we have a non-normal population. So first of all, let's remind ourselves about what statistics we tend to use to describe sets of data. The most common ones are the mean and standard deviation. For the sample mean, we use the symbol x bar. Why is it called a statistic? Well, if I take a random sample and I look at the average, and somebody else takes a random sample and looks at the average, most likely they're going to be slightly different numbers. Since that makes the process of finding the average a random process or a variable process, there is a distribution of the numbers that we would get through that process. Because it is a variable, it will have its own probability distribution. So in this section, we're going to look at what shape does that distribution have if we were to repeatedly take samples of the same size from a population. So the sampling distribution will be defined to be the probability distribution of that statistic for all possible values of the statistic computed from a sample of size n. So the sampling distribution of the sample mean, x bar, is the probability distribution of all possible values of the random variable x bar computed from a sample size of size n from a population with mean mu and a standard deviation of sigma. Again, remember that the underlying population will have a specific mean, and it will have a specific standard deviation. We most likely will not know what those are. That's the whole point of us taking random samples and looking at the average of that sample, is that we would like to estimate that population mean by using the sample mean. In a similar fashion, when we take a random sample and we look at the sample standard deviation, we're approximating the standard deviation, the standard deviation for the population by that sample standard deviation. Again, statistics are data obtained from a sample. They are used to estimate parameters or characteristics of a population. Because the process of taking a random sample introduces variability into our method, different people to get different samples will have different sample means, and the distribution we would have from looking at all the different possible sample means is called the sampling distribution of the sample mean. So now we need to describe what we mean by, or what the distribution will look like in two different cases. One when we have a normal population, and one when we have a non-normal population. A normal population is one where we have our nice bell-shaped curve. Now, it makes sense that there would be a relationship between the standard deviation, or the sample mean and the population mean, and the standard deviation of the sampling distribution and the standard deviation of the population. Why would there be a relationship? Well, each time I take a random sample, I'm estimating that population mean by looking at the sample mean. in order for that to be a good estimate, that would tell me that they would need to be somewhat related to each other. The more samples I take, the better idea I'm going to be able to get of what the true population mean is. So if I were to take an infinite number of random samples, if it were possible, and look at the average of all of those random samples, or look at the average of the sample averages of all those random samples, then that should match up with what the population mean is. So again, the distribution of the sampling mean, or the sampling distribution of the sample mean, should have a mean equal to the population mean. That's because, again, each time we take a random sample and measure its mean, we're estimating that population mean. In order for that to be a good estimate, if we were to repeat this process over a long period of time, we should end up approaching the population mean. In a similar fashion, with the way that the data is arranged, it has some variability in it. Because there's variability in the data itself, that also relates to the variability we would get in the sampling process. So it makes sense that the more variability there is in the underlying population, the more variability we'll see between samples. We're going to look at some examples now to see kind of what effect sample size has on this, though. Okay. So let's say we took the weights of pennies minted after 1982, and that we know that those are approximately normally distributed with a mean of 2.46 grams and a standard deviation of 0.02 grams. We're going to repeat the sampling process by taking 200 simple random samples of size 5 and measuring the average weight of each penny, and then looking at the average of the averages and the variability from those averages. So again, we're going to take 5 pennies, we're going to weigh them. From that weight, we'll get a sample mean. Once we've taken the 200, we've done that process 200 times, we'll now have a set of data that has 200 numbers in it. Each one of those numbers represents a sample mean. We're then going to take the average of all of those to come up with an estimate of the mean of the sampling distribution of the sample mean, and we'll look at the standard deviation of that set of 200 numbers. Okay. So for our first example, let's say we took our 5 coins and they had the following weights. If I calculate the sample average there, that gives me a sample mean of 2.479. Okay. Now we'll repeat that process 199 more times, and we'll get this table of values. So each one of these values would represent the sample mean we got from taking a sample of size 5. If I take the average of those 200 numbers, we get an average value of 2.46, which is the same as the population mean. Again, shouldn't be a surprise there, because each sample mean is approximating that population mean. So if we repeat this process a large number of times, the average I get from that process should match the population. But let's look at the standard deviation. The standard deviation of that set of 200 numbers is 0.0086. Which is smaller than the standard deviation of the population. We'll talk about why that makes sense when we show the formula that gives the relationship. So the next slide is our histogram of the sample means. Notice that it is somewhat bell-shaped. So let's look at what role n of the sample size does play in the standard deviation of the distribution of the sample mean. As the sample size increases, the standard deviation of the distribution of the sample mean decreases. Let's think about that for a minute. Well, if I have a set of data, that data has some variability in it. We can measure that variability by looking at the standard deviation. Taking random samples is also a variable process. The more spread out the data is from which I'm taking a random sample, the more spread out the sample means will be in doing that process. However, the larger the sample size I get, the more information I have going into each one of my samples, the less variability I'll see between samples. Again, the more information I have, the better the decision I can make. So I have less variability in my observations. So the larger the sample size, the more information is used to calculate the sample mean in each sample, the better that approximation is going to be then of the population mean. So the less variability I'll get between samples when I repeat the sampling process. For example, let's take our same coin example, but now increase the sample size to 20. What we'll see is that we still get the same sample mean, or the mean of the sampling distribution of 2.46. So we did this process 200 times again, but now we looked at 20 pennies each time. We still got an average of averages of 2.46, which matches the population, but the standard deviation decreased by about half. As expected, because we had more information going into each random sample, our sample averages were a better estimate of the population average in each case, so there's less variability between samples. So we had a smaller standard deviation between samples when we had a larger sample size. So now comes the payoff. How do we know what the mean of the sampling distribution is for the sample mean, and what's the standard deviation for the sampling distribution of the sample mean? Well, let's suppose that we have a simple random sample of size n. It's drawn from a large population with mean mu and a standard deviation of sigma. The sampling distribution of x bar will have the mean mu sub x bar equals mu, and the standard deviation equals sigma sub x bar is sigma over the square root of n. Okay. So let's try to put that in English. Okay. What that says is that the mean of the sampling process should match the mean of the population. Mu sub x bar is the mean I get from the sampling process. So each time I take a random sample, I get a sample mean called x bar. If I repeat that process a large number of times, that distribution will have its own mean. We denoted that by mu sub x bar. Because the sample mean is estimating the population mean, if I repeat that sampling process a large number of times, I should get something that mirrors the population. So the mean from the sampling process is the same as the mean of the underlying population. In a similar fashion, this standard deviation is a measure of variability or dispersion, right? It's on average, how far away from the mean do the points lie? Sigma sub x bar is a notation for the standard deviation from the sampling process. Again, each time I take a random sample, I'm going to get a sample mean. But two different people taking two different samples will get two different sample means. So there is some variability within that process. So the standard deviation of the sampling process, sigma sub x bar, should be related to the standard deviation of the underlying population. The more variability there is in my underlying data, the more variability I'll see in my sampling process. Where does the over square root of n come from? Well, this is again taking into account that the larger the sample size, the more information that's going into each sample, so the less variability I'll see between samples. And it's an inverse relationship then. And we actually saw this in the previous one. We had, when n was equal to 5, we had a standard deviation of 0.0086. When we increase the sample size by a factor of 4 and raised it to a 20, we got a standard deviation of the sampling process of about 0.0045, which is roughly half of that. Remember, 2 is the square root of 4. So if I take 1 over the square root of 4, that would be a half. So the standard deviation I get from increasing the sample size by a factor of 4 decreases the standard deviation of the sampling process by a factor of a half. So we call x bar so the sigma sub x bar is the standard deviation of the sampling distribution. It's also called the standard error of the mean. When you run some things on StatCrunch later on, you'll see a column, and you actually even already seen some of this before when you looked at the linear regression. There was a column that had standard deviation, and then next to it, it had standard error. The standard error was the column that would have given you the error or the standard deviation of the sampling process. If the random variable is normally distributed, then the sampling process also follows a normal distribution. So the distribution of the sample mean is also normally distributed. So if I start with a bell-shaped curve, the sampling process will give me a different bell-shaped curve. So if we look at the weights of pennies minted after 1982, it's approximately normally distributed. I want to know what's the probability that in a simple random sample of 10 pennies minted after 1982, we obtain a sample mean of at least 2.465 grams. Well, I know that the underlying population is normally distributed with this mean and this standard deviation. I'm now looking at taking a process of taking random samples of size 10, and I want to look at what's the probability that the sample mean that comes out of that sampling process is at least 2.465 grams. So what I'm looking at is trying to come up with, find the probability that x bar is bigger than or equal to 2.465 grams. Okay. Well, because I know I started with a normal distribution, I know finding probability here will relate this back to a standard normal curve. To do that, I have to figure out what the normal or what the mean and standard deviation are for this sampling distribution. Since the pennies were normally distributed with a mean of 2.46, I know that the sampling process will provide a mean of 2.46 as well. So I know that mu sub x bar is 2.46. I know that the standard deviation or standard error of that sampling process is the standard deviation of the population divided by the square root of sample size. So it's 0.02 over the square root of 10, which is 0.0063. So now the question is really, let's find the probability that the variable x bar is greater than 2.465, knowing that the population mean is knowing that the mean of the distribution that we're looking at is 2.46, and the standard deviation of that distribution is 0.0063. So we can still use the fact that z equals x minus mu over sigma. And we would use it's in terms of the distribution we're in. It's using the sampling distribution of x bar. So we're really looking at x bar minus mu sub x over sigma sub x bar. Or if we prefer, we can say we want to put it all in terms of the original population. It's going to be x bar minus mu over sigma over the square root of n. Okay. We've gone ahead and done the calculations here, so it's a little easier to plug in. We went ahead and figured out what sigma over the square root of n is 0.0063, so that it looks more like what we did previously with our calculations of the normal distribution. So we end up with converting the x bar value of 2.465 to a z-score by subtracting away the mean and dividing by the standard deviation of the sampling distribution, giving me 0.79. So now I want the probability that z is bigger than 0.79. That's this area to the right here of 2.465. That's the opposite of the area to the left. So we're going to look up in our table. We'll see that the probability of being less than 0.79 is 0.7852. I'll take that away from 1, and I get 0.2148. So this is the same as what we did in lesson 6. The only new thing is that we had an extra step here of determining what the mean and standard deviation of the sampling distribution was. Well, now let's look at what happens if the distribution of the sample mean is non-normal. Let's take, for example, the discrete distribution where we roll a fair six-sided die. The average value of that is 3.5, and the standard deviation is 1.708. Because this is a nice uniform distribution, well, a discrete uniform distribution, because each value is equally likely, my histogram is certainly not bell-shaped. But what happens as we start taking random samples? So let's take a random sample of size 4. So we're going to roll the dice 4 times, and based off of those 4 values, we're going to calculate a sample average. We're going to do that 200 times. We're then going to repeat the process for n equals 10 and n equals 30 and see what happens. Well, if I roll the die 4 times and take its average, That gives me a sample average that's estimating the average for the overall distribution or overall population. And even with just sample size of 4, we can see that the sampling process does create something that is bell-shaped. It's not, each value was not equally likely in this average. Through the process, we were narrowing in on the sample average of 3.5. If I look at n equals 10, it becomes even more bell-shaped, and it becomes a little skinnier. We're further narrowing it out on it. And if I look at n equals 20 or n equals 30, it's very nice and symmetric. And so what we end up with from this example is an illustration that shows us it doesn't matter what the underlying distribution looks like. If I take a large enough sample, the sampling distribution will always have a shape that is approximately normal. And it will still have the same characteristics that we had before. The mean of that sampling process will close in on the mean of the population, and the standard deviation of the sampling process will be related to the standard deviation of the underlying population and will still satisfy the relationship that the standard deviation of the sampling distribution is sigma over the square root of n. This is what's called the central limit theorem. It says the central limit theorem says that the shape of the distribution of the sample mean becomes approximately normal as the sample size of n increases, regardless of the shape of the population. So no matter what distribution I start with, if I take a large enough sample size, the sampling process will mirror a normal distribution, or will be approximately normal. In the next section, we will start talking about what we consider normal enough, or what to do if we have a sample size that's not quite big enough. In general, we tend to regard a sample size bigger than 30 as being of large enough size that the underlying sampling process will have a normal distribution. So let's take an example of the central limit theorem. Suppose that the mean time for an oil change at a 10-minute oil change joint is 11.4 minutes with a standard deviation of 3.2 minutes. If a random sample of n equals 35 oil changes is selected, describe the sampling distribution of the sample mean. And if a random sample of 35 oil changes is selected, what is the probability the mean oil change time is less than 11 minutes? Well, from the sampling process, we know there's some variability. The more samples we take, the closer we'll close in on the population mean. So the mean of the sampling distribution should be the same as the mean of the population. So mu sub x bar will be 11.4. The larger the sample size, the more, or the closer together each of our samples will be, so the less variability we'll see. And so we'll get a standard deviation of the sampling distribution equal to the standard deviation of the population divided by the square root of the sample size, which is 0.5409. So we know from this process, because we took a sample of size 35, that regardless of what the underlying distribution looked like, the population, or the sampling distribution of the sample mean, is approximately normal with a mean of 11.4 and a standard deviation of 0.5409. So now if we want to know what's the probability that I'm less than 11.4, we're going to go back and do the same thing that we did before. I'm going to convert the 11 to a z-score. So I'm going to take 11 minus the standard deviation we have for our distribution of 11.4 divided by the standard deviation of that sampling distribution, which is 0.5409. So this gives me a z-score of minus 0.74. So now I want to know the probability that z is less than minus 0.74. I'll go to my table, I'll look up minus 0.74, and I'll see a value of 0.23. So that ends our first discussion on the distribution of the sample mean. Next time, we'll begin talking about how can I use the sample means to give me a range of estimates of what I think the population mean might be.